All right. So yes, today I'm going to talk to you about the inherent genetic control of sesame and the impact on root architecture and how root architecture relates to canopy development. And so this is a research that I have been working on with Diane Rowland for the past few years. And so I will be presenting the results today. So first, we come from the University of Florida, and what people know about Florida usually is Disney World. But we have actually much more to offer than this. We're also very famous for our citrus production, although in the past 10 to 15 years, we've been hit by the citrus greening disease, which has completely decimated how citrus grows. And today we have 100% infection over the entire state. So this is sadly much more representative of what citrus growth looks like these days. And in terms of economic losses, it's over $8.5 billion and over 31% in losses in net production. So it's a huge problem. And so we have to find solutions for growers facing this issue. But Florida is also known for a wide network of underground springs, and it's very pristine water. It's very beautiful. Just on the north central part of Florida alone, we have over 700 springs. So it's a very dense network of water, and of course everything is interconnected. Florida is kind of a big sponge, and so and a lot of these springs are also habitats to a wide variety of animal and vegetable plant species. And of course that causes, there's issues and threats with agricultural production in terms of water quality and also water use, because most of the water we consume is in the cities, and clear water comes from this spring network. So, as I said before, the citrus production has been hit by this disease, so we need to find alternative crops for the Florida citrus industry. And so some of the characteristics these crops must have are drought tolerance, because we want to reduce the impact of agriculture on the water system. Water resilience, because climate change, and so we are faced with more irregular rainfall, and also low import requirements, again with this water quality issue. And if we can find a crop that is able to scavenge nitrogen, that would be a plus. Fortunately, we have sesame. And so sesame is one of these new crops that we are trying to import, if I can say, in the southeast of the United States, because right now almost the entire production of sesame is located in the southwest. And so we are trying to bring that into the southeast based on the multiple benefits that it has. It's drought tolerant, it has low nitrogen requirement, they have some nematicidal properties, so there's a lot of benefits for the crop in the southeast. Just to highlight on some previous work that has been done in the lab looking at sesame nutrient scavenging capacity. So here you have 4 graphs corresponding to 4 different cultivars, and you can see, you can't see, but I'm telling you that the nitrogen here, the amount of nitrogen that you can see here are superior to the nitrogen amount that were applied to the crop. So it's effectively able to scavenge nitrogen from the soil. And because it's an annual crop that dies at the end of the cycle, of its growing cycle, it's shedding all of its leaves, and that organic matter that is redistributed to the soil can potentially be available for the following crops. So, but today, because it's the root conference, I'm going to focus on the diversity in sesame root systems, because as I mentioned before, it's a new crop for the area, so there's a lot of things that we don't know about the crop, and that, of course, encompasses the root systems. And so I'm going to present the results from a trial that we ran over 2 years in 2013 and 2014 over 6 sesame cultivars that are non-dehiscent. And this is an important keyword here, because 95% of the sesame in the world is harvested by hand, because it's a dehiscent crop, meaning that the capsules open at the end and the seeds fall off, so it's very hard to mechanically harvest. We are lucky enough in the United States to have a company called Sesame that breeds specifically for non-dehiscent cultivars that are able to be mechanically harvested. So these cultivars come from this company. So there are different genotypes, but on the scale of the germplasm available in the world for sesame, they're still relatively similar. And so this experiment focused on rhizotron, which I'm not going to present. Well, the system, all know how it works. And also, we looked at the relation between the rhizotron images and the leaf area index, so below and above ground biomass. So first, some very big picture thing. Are there any differences in cultivar, between cultivars in total root length? So as you can see here, no, there are no differences in cultivars when looking at the root architecture pattern. Oh. Okay. However, there is some variability among the soil depth, which is only one element of root architecture, but of course not the whole picture. So then we try to look at, speaking of the whole picture, taking some bigger approach and looking at a multivariate analysis, which is a canonical discriminant analysis. So not to go too much in details, but out of the 6 cultivars that we had, you can see that two of them were separated from the cluster from the second axis, which corresponded to shallow rooting parameters. So meaning that these two cultivars, EX5 on the right and S36 on the left, had more roots in the shallow depth. But also these two cultivars are clearly separated along the first axis, which is the total root length and surface area between 20 to 30 centimeters. So these cultivars seems to be different from the 6 others. So when we look more into details, focusing on the proportion of total root length per diameter class, we see that for EX5, we have the bulk of the roots are centered between 2 and 3.5 millimeter in thickness, with a non-negligible part of very thick roots above 4.5 millimeter in diameter. S36 is slightly different with a peak at 2.5 millimeter, and most of the 3 bigger categories being 1.5 to 3 millimeter in diameter. So it seems that there are differences in fine roots between these two cultivars. And with fine roots, we kind of want to look at turnover, because sesame, as I mentioned before, is an annual crop, and so it senesces in the field. And thanks to the mini rhizotron system and the Win rhizotron software, we're able to categorize the roots between live roots that are really bright, white, and turgid, to senescing roots that, I don't know if you can see clearly on the image, but it's slightly thinner, and you can see some black dots inside the roots, which we assume are still functional, but to a lesser degree than the live roots, and then dead roots all the way to the right, where you can barely see the root. It's super thin, super dark, and completely dead. And so obviously these are the same. These are the same locations imaged 3 times throughout the season. So because we're able to access this root turnover to measure it, this is what we see. So this is across cultivars, because we wanted to show you the overall trend across these cultivars, to see that they start senescing their roots as early as 8 weeks after planting, and it reaches a peak at 13 weeks after planting, and accordingly to the senescence, then the amount of dead roots increases throughout the season. All right, so yep. So then if we focus on these two cultivars that I mentioned before, EX5 and S36, and we look at the percentage of total root senescing over time, we can see differences between these cultivars. EX5 really senesces at the end of the season, waiting until 17 weeks after planting to really, starting to senesce its roots at a high rate, whereas S36 starts much earlier in the season, and it has kind of a steady increase well, not steady, but it just increases at each time period. So then potentially that can have an impact on the above ground biomass because one cultivar is losing its roots faster than the other cultivar. But if we look at LAI, we see that S36 is maintaining its LAI longer than EX5. So one hypothesis here is that because of the root senescence, it allows for reallocation of some nutrients to the above ground part, and then allowing the canopy to be maintained longer. And also, so we only represented these two cultivars here, but S36 was kind of really stood out from the masses of the 5 other cultivars, which were much similar to EX5. So that's interesting because it gives, that means that there potentially is a genetic control of the root senescence and the impact that it has on the above ground biomass. And if we can see these differences in this set of genotypes that are very relatively close together, then we can only imagine what we can find if we were to screen the entire, well, not the entire because there would be a lot, but more germplasms, more sesame plants genotypes across the world. So some of the impacts of this research. So it's the first fundamental information on root differences among sesame cultivar over time. Sesame literature is very scarce, and especially when you look at roots. So this is the first insight as to what is actually happening. It's also, as I mentioned, a base for breeding information for developing regional specific cultivars. And all of this research and what's going to happen in the next few years on the crop is going to be fed into improving a decision support tool called Sesame Farm, which is an irrigation model that we're trying to develop for farmers because they don't have experience with this crop. So we really want to help them achieve a good crop in regards to the water management. And so part of this Sesame Farm improvement model comes from another set of trials that I'm not presenting here, but I will have a poster on it tonight. So you're welcome to stop by and look at very pretty root pictures. But I mean, you've already seen a lot, but you can always have fun looking at more. So thank you very much for your attention, and I'll let you take questions.